Thank you very much. Is the microphone on?
Yes.
Thank you. Yes, good morning. So welcome back from the rigors of last night's wonderful entertainment, back to the rigors of scientific discourse. I'd like to thank the organizers for the opportunity to participate and to contribute to this event, which I feel looks very much in two historical directions at once. On the one hand, we are celebrating 40 years of the prediction of Hawking radiation and the way it has influenced the way how we think about quantum fields in curved space-times, even quantum fields in flat space-time, and how it's influenced our thinking about the questions that a quantum theory of gravity should eventually answer. And this lecture room puts us in very appropriate mindset of reverence for that point of view. But on the other hand, we are also keenly aware that there are questions that we are here trying to address, and we will be addressing them in the future, in the coming decades, certainly. Perhaps already questions about the formation of black holes, what happens to black holes while, if we assume that black holes do form in a more or less conventional fashion, how they behave while they radiate, and what is the end point of Hawking radiation. And it is to those questions that I'd like to contribute today. So this talk is based on three papers mentioned here. Edu Martin Martinez is a senior postdoc at the Institute of Quantum Computing at the University of Waterloo. Eric Brown did his PhD at the University of Waterloo, is now about to start a postdoc in Spain. Right, so sorry about the somewhat frivolous title. The title is a question with a yes-no answer. And it has been observed that whenever the title of a scientific paper or a talk is a question with a yes-no answer, the answer tends to be no. Today, I'm afraid I will have to disappoint you already before the actual talk begins. My answer will be a qualified yes. So in the title there is this buzzword firewall, which previous speakers have already alluded to. And this has to do with the behavior of macroscopic black holes as they Hawking radiate. There have been suggestions over some time, and many persons in this room have contributed to those suggestions, as to what might be happening at the horizon of a Hawking radiating black hole. And in the last few years, there has been a crystallization of these suggestions under this code word firewall. So previous speakers have alluded to this, but I think I should start by doing a brief recollection of what this buzzword means and what the issues are about the horizon of an evaporating black hole, and why there are suggestions that something catastrophic, something drastic might be happening at the black hole horizon, even when the black hole is still macroscopic. Maybe I should say I will not necessarily be advocating that this is the correct way of thinking about things, but I will be reviewing the arguments that have been proposed. And then I'll be looking at some model calculations. I'll present three pieces of evidence of what actually happens to someone who falls through a firewall, assuming the basic quantum mechanical picture behind the firewall argument is correct. The fine print is I'll be entirely ignoring gravitation. This is a field theory calculation, assuming our thinking, the firewall thinking about the quantum field side of the problem is correct. How bad is the quantum field theory singularity? And on that side, the conclusion will be, it will not be very bad if you send a atom, well, let's say a chicken, through that sort of a firewall. It may get its feathers a little bit ruffled, but it will not get blown to smithereens, and it will even retain most of its memories of the outside world. It's not the quantum field theory side of these issues that is singular. If there is something truly singular going on, that singularity will need to be on the truly gravitational side. And that will be the overall conclusion. Okay, so that's the plan. That's my plan anyway. Now, I am aware of the expertise in this room. Any comments, objections at this point? Okay. So anyone who has got a speeding ticket can appreciate that when there is some kinematics taking place in space-time, say the front bumper of your car, that kinematics has an influence on quanta that exist in the space-time. And this has consequences, even financial consequences. And these observations predate quantum theory, they predate relativity. There's basically a Doppler shift effect. But when you are working in a relativistic quantum field theory, then things get more exciting. It's not just that a pre-existing quantum can change its quantum numbers. It is that where originally there were no particles, there suddenly can turn out to be particles, and there can be turn out to be an energy associated with them. Right? So one of the early pieces of information, early observations, has to do with a moving boundary in Minkowski space. The observation there is if you move a reflecting boundary, that does create quanta. It does create an energy flux, and many persons in the room have contributed to this topic. This is often called the dynamical Casimir effect, sometimes the Davies-Fulling effect, and so on. And so this is a prediction of a mechanically moving boundary. If you put in the numbers, it's hard to move a mechanical boundary quickly enough to get actually observable numbers. But similar things happen in microwave cavities, where you can modulate a boundary condition electrically without actually any mechanical motion. And a few years ago, this was observed in an experiment in Sweden at Chalmers. So although the dynamical Casimir effect in the mechanical context is still elusive from the observational point of view, the analog system, there this has been experimentally confirmed. Now, another setting about which we have been reminded over this meeting is the cosmological particle creation. Particles do get created by the expulsion of space-time. And, well, has this been observed? Arguably, yes. We are here, after all. And there are strong suggestions that our very existence is due to those cosmological fluctuations. But I'm not going to address either of those two things. I want to talk about the black hole radiation, so Hawking's prediction. So assuming the conventional picture holds, the calculation says you take a collapsing star, quantum matter, say the electromagnetic fields, and at early times a usual vacuum, say no incoming particles. Then Hawking's calculation and the elaborations that were done on it at the same time, there is a prediction of a flux of radiation out of the black hole. Now, you may not be able to say exactly where the particles are near the black hole, but there's an unambiguous flux that goes with it, and that flux carries energy out of the black hole. The black hole must respond to this, and the conventional way of thinking is, well, as long as the black hole is macroscopic, it slowly shrinks, but nothing drastic should happen at the shrinking horizon as long as the black hole stays macroscopic. So this is the conventional picture. And there have been challenges to this picture coming from, from various points of view over I guess, over the past decades from various grounds, including persons in this room. But I'd like to draw a space-time picture of a recent crystallization of these ideas that something might not be quite right. And it has to do with the end state of black hole evaporation. So suppose that evaporation preserves unitarity and the black hole disappears. Here's a space-time picture of what the process might look like. I want to talk about early and late times, so I want to be careful about that. And for me, early and late times means certain space-like hypersurfaces. There is an early space-like hypersurface. That is when the black hole has not yet formed. Perhaps there is a collapsing star there present, but not yet collapsed. Perhaps there is some gravitational radiation that forms a black hole. Perhaps there is a set of operating TV sets that is forming the black hole. But somehow the black hole gets formed. There is the horizon. Then there is a somewhat later time, later space-like hypersurface when the black hole is there. It has started to radiate, okay, and these lines depict the radiation. And as has been discussed over this meeting, you can't really say that here is a particle that gets created. So it's somewhat ambiguous, which I've tried to ambiguous in terms of particles, as I've tried to illustrate here. You can talk about the energy in an unambiguous way, and there is an energy that is going to infinity that way. And then we're assuming at late times there's no black hole left. There is a late time space-like hypersurface. We see there the radiation that has come out of the from the black hole. Some of it has made quite far. Some of it has not made quite that far from the inner regions of the space-time. But this is a regular space-time over here, and that is a late time for me. So the basic assumption is there's a pure state here. We started with a pure state over here. What does this imply with our thinking about the correlations present in Hawking radiation? So we're assuming at late times there is a pure state. Nevertheless, Hawking's calculation tells us that if we look at the early time Hawking radiation over here, it looks approximately thermal. It looks like a mixed state. Okay. Then there is a later time Hawking radiation over there. It looks also thermal in a higher temperature, okay? But it does look thermal. Yet the overall state, by assumption here, is pure. The only way a pure state can look thermal when you look at it in some subregion is if there are strong quantum mechanical correlations between region here and region here. So this is a fact about quantum mechanics. It looks mixed over here, mixed in a thermal way. It looks mixed over here, but overall it is pure. There has to be a certain kind of strong correlations here. And you can put technical language on those strong correlations, and you can put technical language on where your optimal split is between early and late. And let me not get into any of that. So that's the first assumption. You've got a pure state over here with Hawking radiation going out. Next step. So I would argue by this point we're entirely innocuous. If you buy the top line, what I've said so far should be uncontroversial.
But why do you insist on having a pure state on sigma 2?
Right.
You might want it on sigma 1, but it must necessarily survive what's going to happen.
Yeah, shall I repeat that into the microphone? Why do you insist on having a pure state on surface sigma 2? I can understand that you start out with one on sigma 0 and it stays still pure on sigma, well, all right, on the whole of sigma 1. But why, it's an assumption that it will be pure on sigma 2, is that right?
It is an assumption, so we are saying, suppose black hole evaporation preserves unitarity.
Right, but isn't that what we're trying to establish?
So we are trying to see what that assumption leads to. I will review in a few moments that something will go wrong in the set of arguments that I want to present. And I was about to say that if we took a poll in this room as to what it is that goes wrong, we would get a number of votes for the top line, that something goes wrong already there. And so I'm very happy you are raising this point.
Right. Because at the very least, you've got the singularity there, and that can't be ignored.
Right.
You may say that singularities don't really exist, but as you put it in, it clearly is going to be part of the story here.
Right. So at this point, we don't really know what should be happening. That would require a real theory of quantum gravity.
Exactly.
And in your book, when you draw this diagram, you put a question mark there.
Right. Very sensible, I think. Yeah.
Right.
Are you allowing possibility of negative fluxes, negative energy fluxes coming into to make the thing consistent?
Right.
Yeah.
So there is a negative energy flowing in the black hole, and I have not drawn that over here. I've just drawn the, as it were, particles that are carrying energy to infinity, the positive energy flux to infinity. Other thoughts at this point?
Is there significant significance to the fact you drew regions B prime and C prime both outside the natural continuation of the original horizon, rather than putting B prime inside that triangle at the top?
There is. So I want to say that C prime looks approximately thermal in a certain early time Hawking temperature. B prime looks approximately thermal in a somewhat higher Hawking temperature, but it looks approximately thermal. Okay. So there has to be strong correlations between C prime and B prime. Over here, we don't quite know what should be happening. I'm assuming there isn't much of interest over there. Perhaps that is another implicit assumption.
Well, of course, as perhaps you're going to tell us later, there are correlations like that in the vacuum in Minkowski space. It's nothing out of the ordinary.
Right. But so what Hawking tells us, there is thermality over here, there is thermality over here, there is some Minkowski things over here, there are Minkowski things over there, and there are Minkowski-type correlations between them. But I'm interested in the correlations that are present in the Hawking radiation, which the calculation says should be there.
Well, just a general comment is that people always draw this Penrose diagram as if classical general relativity held where we know it breaks down, right? Near the singularity and so on. So anyway, it's a peeve of mine.
Right, so I'll comment on that in just a moment. In fact, I'll comment on that now. So there's the late time hypersurface. So now let's think about what the quantum fields look like on this medium time hypersurface sigma 1, where some Hawking radiation is already present, but the black hole is certainly present. We don't know what happens very near that corner, as has been emphasized. But suppose I'm not going very near that corner, I say stay some reasonable distance away from it, and I'm thinking what happens over here on this early time, this medium time hypersurface. Well, here, the space-time should be approximately classical. We are not near the evolving horizon, okay? So we should be able to use the equations of quantum field theory on curved space-time to relate these late-time features over here to the early-time features over here. And if you do that, you will then say that by, well, essentially null propagation, these C prime degrees of freedom have approximately come from the C region over here. The B prime degrees of freedom have approximately come from the B region over here, at least provided I'm not going very, very close to the horizon over there. So whatever the correlations between B prime and C prime were over there, then assuming the semi-classical picture of the space-time is valid, those same correlations between B and C should be present over here, and they should be strong. If they were strong over here, they should be approximately equally strong over here in an appropriate technical sense. So that's the second assumption that goes into this game. And I would argue it is innocuous, provided you are not going very close to that corner of the diagram.
I think the main objection against this whole picture is that the space-time metric itself is also an operator field. And what you've done by drawing a Penrose diagram is you've diagonalized that operator. So you look at the frame with that operator as diagonal. But in that frame, you cannot also assume that all the physical particles are in their energy eigenstates or anything like that. When you assume that, you are disobeying the uncertainty relation. So I think it's the main, I think that might well be the cause of all the difficulties we have with this picture.
Agreed. So this picture does assume the semi-classical picture of the space-time is essentially valid, and that could be a source of problems. Okay, but nevertheless, let me push on with the argument. So, so far, so good. Now, the issue is, if we go back to Hawking's calculation and the papers by Parker and Wald and others that elaborated on it, why do we think that there's Hawking radiation here in the first place? Well, the calculation says that the, as it were, particles here in B, they are already strongly correlated with something else, and that something else in a certain sense is localized over here. This is what Klaus Kiefer was referring to in his talk when he talked about those two-mode squeezed states. So there are already strong correlations with the B and something else, and in a certain sense that something else is over here. And now something has gone wrong, for there is something called the entanglement monogamy theorem that says if whatever degrees of freedom you have in B are strongly correlated with C, then they can no longer be strongly correlated with A in an appropriate technical sense that I won't try to elaborate on here. So this just such strong correlations just can't happen between both B and C and B and A. So this is the paradox which Almheiri et al. Highlighted a few years ago. And the argument is something in this picture has gone wrong. And we've heard suggestions as to what it might be that's going wrong. And earlier this week, we heard a new suggestion from Stephen Hawking saying, maybe what's missing from this picture are degrees of freedom that live here, essentially on the horizon, and have to do with the super translations. And if Stephen's suggestion is correct, then, well, we could basically stop the talk over here and say that that was the resolution. Well, I would like to review here the resolution that Almheiri et al. Proposed. Now, they said, maybe it's the correlations between B and A that are somehow broken down by some drama that takes place on this horizon already when the black hole is macroscopic. And they dubbed this firewall, and this is related to earlier work by a number of people. I've mentioned a few of them here. So the idea is something in the evolving horizon goes so drastically wrong that the correlations between the interior and the exterior of the black hole are completely broken. Okay. It's a drastic suggestion, has been widely debated in the literature. It's very hard to get a calculation going about this. And the problem is that it has to do on both the quantum mechanical side of things. The argument says the quantum mechanical correlations must break down, But then there's this evolving space-time under it, and the breakdown of the quantum mechanical correlations must affect the space-time in some sense, and it's this interplay that is very difficult to model. There are a few model calculations about this, but maybe I'll mention something about them later, but it's very hard to get a calculation going.
So my question is, where does the energy for the firewall come from?
Right.
There's no obvious source for it. I mean,
Right. It's hard to get a calculation going.
Maybe I'm just muddled now because we've heard so much of this, it has that effect. But is it not the case that the correlations between A and B are destroyed by decoherence? Destroyed by what? Decoherence, because so if you have an entangled pair and one goes down the black hole and the other doesn't, the entanglement is lost because of decoherence due to the Hawking radiation. That's a sort of simple statement I've heard people make. Same is true in de Sitter space. So, did I just get that wrong, or is that part of this story? Does that simply resolve what your problem is here? Yeah, I mean, are you talking about entanglement? Well, you are talking about entanglement, not just correlations. You're talking about entanglement between A and B. So if you're thinking in terms, so I'm a bit confused. Is this intended to be like a pair of particles that are entangled, and not just a correlation between two different outgoing particles? Because B and C are both like outgoing particles. What are B and C, actually? Sorry to keep asking all these questions together. So B and C, these are blobs, but are we talking about outward moving particles? Or
Right, so I've drawn B and C as sort of regions on this space-like hypersurface.
Right.
Okay, and A as a region on this space-like
I'm not
hypersurface.
too sure what that means.
Right, so the thinking is in terms of localized wave packets. And we think of them as the correlated particle pairs that appear in the two-mode squeezed states in the standard picture of the Hawking radiation. Right, I am aware that it's difficult to make that sense of localization there fully rigorous as well.
But is everybody here agreed on the simple statement, which is that if you have an entangled pair and one goes down the black hole, you lose the entanglement by decoherence? Maybe even that is not agreed here.
Well, so this is supposed to happen on sigma 1.
Sorry,
So this is supposed to be happening on sigma 1 at that particular hypersurface, and you're still supposed to have a pure state over there. Now, if you're saying there is decoherence with some other degrees of freedom, perhaps...
yes. I think that's what the claim is. So there's a particular calculation by Jared Milburn that looks at this, and also for de Sitter space. And that's specifically looking at, so this is really single particle quantum mechanics rather than quantum field theory, at entangled pairs of particles in that background, and looking at the fate of the entanglement, and it decoheres at late times. I don't know how that's... Right, I mean, the simple thing is that the Hawking radiation scrambles the phases. But, you know, I hope I'm not garbling Milburn's result here, but I think that's the gist of it. And it may not be directly relevant to what you're saying, but, you know, whenever I see something inside and outside, and you want it still to be entangled, I'm not sure that that's correct.
Thank you. I should look into
And I'm
that.
just thinking aloud here. I'm sorry to interrupt you, but it seems like a really good opportunity for us to have a discussion of this.
Yeah.
So on the issue of energy conservation, there is another assumption in the points that you have listed that is often not mentioned, which is in the first arrow that you have there, that from the assumption of a pure state, it follows that B prime and C prime are strongly correlated. For this, you don't just need any pure state, but they are using a particular pure state, what they call a typical state. which has some random distribution of the correlations. So if you do not make this assumption, but instead you require energy conservation, then you find a different pure state. And in this state, in fact, B prime and C prime are not correlated. And if you trace it back, neither are, well, B and C obviously, but also A and B are no longer correlated. And in this case, you also don't have a firewall. So what really causes the problem is the assumption that you have this particular pure state.
So does that mean that firewalls are not generic, that you can have pick a particular state which would give a firewall? Was that what you were saying?
There are pure states where you don't have the problems, what I'm saying.
Oh, I see. Some where you don't have
You
a
can explicitly construct them, and the essential requirement is exactly that you have energy conservation. Which is kind of obvious because, as I can't recall who said it, but if you have the firewall, where does the energy come from?
Right, so you can calculate T mu in a two-dimensional model. It's all done. There is no firewall. End of story. So it's only if there's something different in 4 dimensions. It seems very unlikely. Right. Sorry, we've hijacked your talk.
So, Mr. Chairman, how are we doing with time here? Okay. So, right, so none of these are particularly my contributions to the topic. So what I wanted to look at is, assuming the statement about the field theory correlations here is correct, and there is some drastic breakdown between the field correlations, how bad is it to someone who is in the space-time and just couples to the quantum field, but the metric, underlying space-time metric, has not yet had substantial time to react of any pathology that there might be? And so I have 3 pieces of evidence that the quantum field theory correlation breaking, it's not so bad. And let's see how many pieces of evidence we have time to talk about here. So these are 3 model calculations. And the first of these model calculations was inspired by a comment by Bill Unruh about a year ago, saying that, well, if you really want to break a correlation between 2 space-time regions, why don't you just smash in a wall there that separates the 2 entirely? So, well, here's one of my favorite space-times, 1 + 1 Minkowski, and we're saying, let's put a wall there, let's make it a 2-sided Dirichlet wall, and let's make our quantum field to be a massless scalar field, and that way we can get a calculation going. And Bill Unruh actually did a calculation for the case where he puts the wall down instantaneously. And some things go singular when you do that, and the suspicion is, well, how much of that singularity is due to your putting the wall in instantaneously? You would expect things to go wrong. Can you do it in a more controlled way, in some smooth way, and then perhaps approach the rapid wall creation limit in a controlled way? I should say that this does not disentangle what is on the left and right. If you start from, say, the Minkowski vacuum down over here, any correlations that are present in the Minkowski vacuum will still be present after the wall has formed. So this isn't quite a firewall, but it is a similar mechanism. This is a way how to break down any influences between the 2 spacetimes at later, between the 2 halves of the spacetime at late times. And for this, you can get a model calculation going. So we are dealing with a massless scalar field. You need to model this wall in some way, and well, we did it by self-adjoint extensions and so on to control the sense in which the wall creation is smooth. But in physics terms, all it really is you are including in your wave equation a potential term that is a delta function in x, right, with a coefficient that evolves in time, starting from 0 over there, shooting off to infinity over there, and to control the smoothness of that shoot off to infinity, you need to do some fancier language. But that's really what it is, a delta function potential that interpolates between Minkowski and Minkowski with a two-sided Dirichlet wall. And there's some characteristic time scale over which that wall gets created. Okay? And, well, one thing you can calculate is the energy flux. There will be energy going to the left, there will be energy going to the right, and you can ask what happens to that energy when you take the limit of rapid wall creation. The energy, it diverges. So 1 over lambda is that characteristic wall creation scale. When lambda goes to infinity, rapid wall creation, the total energy goes to infinity. So this is a singular limit in some sense. And if you had a theory of gravity that couples to this field, the space-time under that field would eventually react. Okay? But we're saying let's not worry about how the space-time reacts. Let's worry about someone who is going through this burst of energy over there. So now we can think in terms of a chicken, if you wish. Now we did the calculation in terms of something known as the Unruh DeWitt detector. It is a model of a chicken, perhaps a poor model. It's a two-state system and with a certain energy gap, has been much used to analyze quantum fields in that context. And there is a case that these detectors are a good model of the dipole interaction by which the electromagnetic field couples to ions in four-dimensional spacetimes. Well, it's a subject of some fine print. But the argument is this is a reasonable model of a chicken. Okay? And now you ask what happens to the response of the detector when it goes through that burst. And you take the rapid wall creation limit, and you find that the transition probabilities, they remain finite. Okay? There is some probability of excitation, there is some probability of de-excitation, but the chicken does not get blown to smithereens. There is a certain finite probability that happens. So the moral of this example is the sharp wall formation, it is singular gravitationally, but someone who just couples to the quantum field, it's not singular for them. They will feel something, but what they feel, it may be rapid in a certain sense, but it is not singular. So this was example 1. Okay. Example 2. So this is the example that actually got me started in thinking about these things. And so I'm about to describe to you a state in 1 + 1 Minkowski space, again, a massless scalar field, a state that was described to be by Don Maroff, arguing that it is a model of what actually happens in the black hole firewall. And he asked, how does a detector behave, respond in this state? Okay? So let me describe the state here. Here's again 1 + 1 Minkowski space. Okay, with the 4 quadrants as shown, and there's the detector worldline that I'm going to be interested in. Let me recall one fact about Minkowski vacuum. Minkowski vacuum is, of course, a pure state, but if we think of, let's say, the t = 0 hypersurface over here, there are vacuum correlations in it, as has been mentioned. There are correlations between the left and right. And if we start thinking of uniformly accelerated observers who live in this space-time, it is those left and right Minkowski correlations that are responsible for the Unruh effect, for the thermality seen by these uniformly accelerated observers. Okay? So far Minkowski space. Let me construct a new space, a new state. What I'll do is I'll take the Minkowski vacuum as it is in the right, Minkowski vacuum as it is in the left, and by fiat, I'll break all the correlations that exist between left and right. I'll write down a mixed state which in R agrees with Minkowski vacuum, which in L agrees with Minkowski vacuum, but all the correlations between right and left have been broken. It's no longer a pure state, it is a mixed state, but somebody who lives in R would not be able to tell the difference from Minkowski vacuum. Somebody who lives in L would not be able to tell the difference from Minkowski vacuum. The state is somewhat singular, right, as you might imagine. There is a mild singularity on the light cone of the origin. In particular, it is non-Hadamard, which means that you don't really know how to talk about the stress energy tensor. So gravitationally, this state would again be singular. But we're asking the same question as in the first example. Suppose you let the spacetime stand as it is, the spacetime hasn't yet reacted, and you let your detector go through this singularity over here. How does it respond? And so this is the only complicated formula I'll show. So if you're already in Minkowski space, there's a certain response of a detector. So the formula here is the difference between the Minkowski response, Minkowski vacuum response, and the response in this firewall state. Right, so there's technology there. Omega is the energy gap of the detector. Then chi is the function that tells you how the detector is switched on and off. T equals 0 is when the detector crosses that future horizon. And right, so that is what the response is. Any questions?
Oh, yes. Is the detector crossing at the place where you had the green line in the previous diagram, not through the origin coordinates?
Not through the origin, although if it did cross through the origin, you would get twice this.
That's what I'm worried about, yeah, okay.
Yeah, you'd get exactly twice this.
Right.
So, yeah, so it crosses over there. It's turned on somewhere over here after, so that it doesn't cross the early part of this horizon. The only crossing of the horizon occurs over there.
Switch it on slowly and then let it cross.
You switch it on and off slowly as controlled by this chi, this switching function. You can think of it as a smooth function of compact support if you wish. Right, so any questions?
Yeah, you have to propagate into the upper region
Yeah.
from the left and right
Yeah.
wedges. Is that straightforward? I mean, that is the state. You've defined the state in the left and left and right wedges, and then by some sort of analytic continuation into the region above.
By null propagation, by using the wave equation. Now, the state is right. So there are some things that propagate from the right, some things that propagate from the left. So you are using the field equation and the knowledge of your initial state. At the origin, something funny is going to happen, and the input we used is that at the origin there is nothing more singular than this construction requires.
But is this a unitary propagation? Because that's what we're trying to sort out.
The state is somewhat singular, so I'm not sure whether to think of it in terms of unitarity.
Well, that's what we're up against.
Okay, so there's the formula. Did the detector get blown to smithereens? You might be worried about this one over S squared things and over there, but no, it's okay. It's some finite probability. And you can then think about where these various terms come from, and you can separate them into a sort of sharpish kick at the firewall crossing and the absence of correlations before and after the crossing and so on. And you can think about the large energy behavior and certain logarithmic behavior, and there is some fine print as to which sort of Andrew-DeWitt detector you use, but let me not get into that here as I'm essentially out of time anyway. So the overall conclusion is something singular happens, but the singularity is not catastrophic to the detector. Now, I'm almost out of time, so let me briefly say something about the last example. And this has to do with a pair of detectors, Alice and Bob, and you initially put them in a strongly correlated state, in fact, maximal entanglement between those two states. The state of the field is the same firewall state that I've just talked about, and you let the detectors evolve like this. Alice goes through the firewall, Bob doesn't. And we're asking what happens to this initial entanglement over there. And, right. So what's happening is, right now I'm out of time, but what is happening is that on the horizontal axis I have here XA, that is the location where Alice is, and I'm moving this whole Alice-Bob pair to the right. Okay? So XA over there is Alice crosses the horizon. If XA is large, this whole pair is so far to the right that Alice doesn't cross the firewall at all. If XA is small, then Alice crosses the firewall early on. And here's a graph of how the negativity is, or negativity of the end state is, the measure of the entanglement is as a function of XA. The straight line means if Alice doesn't cross the firewall, there's no strong effect. Some effect because of Minkowski space vacuum already has an effect. But if Alice does cross the horizon, there is an effect. I wouldn't take the exact numbers here seriously, but the overall conclusion is the effect is finite. It's certainly not catastrophic. And in a certain sense, it's small. So Alice retains most of her memories of Bob when Alice goes through firewall. There's some modest effect, but not catastrophic. Right, and surprise was that the sign of effect is not fixed, so at least in this model, Alice's memories can actually improve over what would happen in pure Minkowski space. We have no analytic understanding of why this happens. So that was the third example. So I've argued that if the quantum mechanical thinking behind this firewall suggestion is correct, then those quantum mechanical breakings of correlations breakings, they are not catastrophic on their own right. If this firewall is really the resolution to the information loss issues, then the gravitational part of the puzzle, that will need to be an essential part of the puzzle. So is this the right way to think about it? We don't know, and if it happens that the BMS degrees of freedom at the horizon are the right way to think about it, then most of what we have been discussing here will not be relevant at all. We shall see. Sorry about going over time. Thanks for your attention.